Lambda max is the wavelength at which the electron emits the highest intensity when returning to the ground state of a previously excited atom. On a emission graph, it's set up as wavelength versus intensity. Intensity is the number of photons emitted at a certain wavelength relative to the total number of photons emitted. Wavelength represents the wavelength of the photon emitted, which determines the color of the photon emitted. The molecular structure controls the lambda max as shown on this slide, as the red and green dyes both have unique molecular structures and thus unique lambda maxes. The molecular structure determines the available energy states for a valence electron to transition to. Both the red and green dyes have different structures and available energy levels. A simpler example of this can be explained using two atoms. Hydrogen and helium illustrate this idea. Since the helium has more valence electrons, it will also have a higher number of available energy states, as these electrons can jump when excited. Therefore, these same ideas can be applied to molecules, as a more electron dense molecule will have more available energy levels than a less electron dense molecule. These same ideas regarding available electron energy levels exist within the red and green dyes as well. This is why red dye is excited at longer, lower energy wavelengths than the green. The red dye contains more valence electrons than the green, allowing for more available energy levels. Because of this, the red will have a lambda max at a higher wavelength because of less energy is emitted due to an increased number of higher available electron configurations than the green, overall showing how molecular structure determines wavelength at which lambda max occurs. The mixed solution has the same lambda max as the red dye because it contains molecular structures from both the green and red dyes. This disproves the hypothesis because it shows that molecular structure determines the lambda max and not the color. If the color were to determine the lambda max, then the mixed solution would have lambda max at orange wavelengths.
Electrons can be excited just as elevators are able to take people up to another floor. Elevators will go up and down to specific floors based on which button is pressed. Likewise, depending on the specific amount of energy added to an atom, an electron will jump to a specific energy level. Additionally, just like an elevator, electrons will not stop between floors or energy levels, as they require a specific quantity of energy to jump. This is why the peaks occur at specific wavelengths, because wavelengths are inversely proportional to energy. Electrons will not remain at the excited state and will return to the ground state, causing an emission of light. This is like when an elevator returns to the bottom floor to pick up more people. In other words, the ground floor of an elevator compared to an electron at its ground state. For the electron, it's more energetically favorable to be there, as the state requires the least amount of energy. Likewise, for the elevator, it is most likely to be on the ground floor, as that's where most of the people are. This elevator analogy doesn't completely hold, however. For instance, in electron excitation, if an electron is further away from the nucleus, it would require a lesser quantized energy to jump a level, because there's less of an attractive pull on the electron from the nucleus. For instance, the electron would have to absorb less energy to jump from level 1 to level 2 than it would to jump from level 3 to level 4. With the elevator, all floors are shown to be equal distance apart, thus not completely showing the different amounts of energy needed to jump between higher levels as discussed before.